Hello everyone, welcome back. Today we will discuss beta elimination. We started discussing in the last class about the beta elimination. Beta elimination, as you have learned by now, it is a microscopic reverse of the beta migratory insertion, and we have also seen that the intermediate that involves, or this is a 4-centered reaction mechanism that involves this reaction. Now beta elimination, let us try to look back one more time. This is again the microscopic reverse of the beta migratory insertion. Beta elimination involved the metal alkyl species, for example the hydride being the major one or the primary one, and the alkyl over here is less likely, although it is possible. Alkyl is usually less likely, and we have very good examples of the hydride complexes. If this is n electron, this is going to be n plus 2 electron complex. Beta alkyl elimination, let me write that down because that is it's very usual question by the student. It is also known but less common. Okay, let us put it that way, that is easier to remember. Now one thing we can try to discuss, then what would be the preferred geometry, in what scenario this beta hydride elimination will be favored. Of course, I tried to tell you that the beta hydride elimination is so common that it can be nuisance, it can create trouble for a desired another reaction, right. You have a beta alkyl you have an alkyl intermediate. If beta hydride elimination becomes facile, too facile, other reaction which you may be expecting with the alkyl may not be occurring that easily. So beta hydride elimination product gives you a lot of trouble. In fact, a number of cross coupling reactions suffers due to the fact that this alkyl intermediate will undergo the beta hydride elimination. So desired cross coupling reaction becomes extremely problematic. Okay, and that is why one of the reason that sp3 carbon center, that alkyl center, sp3 center, different carbon heteroatom, other bond formation becomes bit of an issue. I mean, it's more than an issue. It is something remained as still challenging after 3-4 decades of research on this field involving cross coupling reactions. We might will discuss that on a different forum, but mainly let me try to put you the idea of a geometrical preference. How can you determine what type of geometry will be preferred, and what could be one of the example for such cases? Geometrical preferences, right. The example we are going to briefly discuss is, let us say you have a platinum complex with 2 ligands, and then you have an alkyl species like that, where it is an open chain process, and beta hydride elimination and subsequent then reductive elimination will give you the product, this one, plus if you do it correctly you will realize that this is going to be the other product, right. So what will happen, that this is alpha, this is beta, from beta, let us say for example beta this hydride, it comes to the here. So olefin coordinated with the hydride, as we are trying to discuss. Remember, let me show you one more time if you have forget. So if you have a metal alkyl species, exactly species, and metal olefin and the hydride intermediate, in this case we have an alkyl extra. So that alkyl, let us say, is over here. Now you have metal hydride olefin and then alkyl. Now these two will reductively eliminate, and this olefin will also fall off from the intermediate. So overall for this platinum complex, as you see, it is a di 1, 2, 3, 4 di butyl complex. Beta hydride elimination and then reductive elimination will give you an olefin and then long chain alkane species. Now that is good. If you have another reaction which is, let us say, of similar type, but in this case you have certain strain in there, and of course you have these are hydrogen, and then the thing is, of course you are going to get the products, beta hydride elimination product. Now in these two cases where you have an open chain starting material, dialkyl or di-n-butyl starting material, and in another case you have the cyclic intermediate where you have the 4-membered intermediate. That means over here you are expecting a 4-membered intermediate, 1, 2, 3, 4, 4-membered intermediate. Actually in this case it is strained for beta hydride elimination, right. So overall what you will see that this 4-membered intermediate one is strained, and therefore it is very slow to undergo beta hydride elimination, because you are not going to get that reaction. The first one where the dialkyl group is there, and it is going to be very facile and there is no strain involved, so it is going to be very easy to deal with. The other one, the second one, since there is a strain involved, that 4-centered intermediate formation becomes very difficult. So the relative rate, if you want to put at relative rate for this reaction, K relative for this reaction would be something like 10 to the power 4 versus 1. So that emphasizes quite a lot of difference of the relative rate, and that is how we would like to call that. In a strained situation, we will have a very slow beta migratory insertion, but in a normal very easy situation that beta hydride elimination is going to be faster. Once again, that is one of the problem rather than a good thing for a lot of cross coupling reaction. Of course, this is a facile reaction, it becomes a nuisance, it creates a lot of side reaction, and we will see why it might further complicate in the next example. The next example we will try to see a very beautiful elegant example which is discussing about the beta hydride beta migratory insertion and beta migratory insertion and elimination occurring in together in one of the example, and how beautifully it can give you the value of this beta migratory insertion and elimination. So application of beta migratory insertion and beta elimination reaction. So we will deal with the Schwarz reagent in this case. That will be the application of beta migratory insertion and beta elimination of course, and this should be all about olefin isomerization. Okay. So what happen is you start with a organometallic intermediate, okay, and in this particular case we will be able to see with Schwarz reagent, particularly zirconium reagent, you will see it is a metal hydride reagent, and then no matter what olefin you take, whether it is terminal olefin, internal olefin, double bond is at the 2-3 position or 4-5 position, eventually you end up getting exactly the same product. That is quite a lot, and I mean it is very interesting. It does not depend on the type of olefin you are taking. The metal alkyl species that you are going to get is exactly same in this case. Type of olefin, I mean that the isomers of olefin. You have a terminal olefin, okay, let us say CnHn, HX. Now another olefin with the same CnHX, but the double bond is now shifted to the beta and gamma position between beta carbon and the second carbon and the third carbon, and then another one between, let us say, 4th and 5th, another one between 5th and 6th, all different olefin with the double bond at different position, okay, exactly same molecular formula, same long chain alkane, okay, but the double bond position is shifting. All of them will give you the exactly same product. That is quite interesting, and that I guess is a very beautiful and elegant example for this beta migratory insertion and beta elimination reaction. Let us try to look at the cyclopentadienyl zirconium, this complex also known as, very popularly known as Schwarz reagent. This is, by the way, done by one of the undergraduate student at MIT. In any case, this is, let us say you have one of the olefin like this, you can have another olefin like that, of course another olefin as you can draw from the same thing is this, right. Overall what you have is a, for all these cases you have Sp2 zirconium chloro starting with this complex 1 2 3 4 5 6 1 2 3 4 5 6. So, this zirconium hexyl complex, N-hexyl complex you are going to get. So, irrespective of those all the olefin that we have drawn 3 different olefin in this case with 6 carbon. The double bond position is shifting, one is a terminal, then the internal, further internal and so on. All the complexes you are going to get exactly same product. That is quite amazing, right. No matter which olefin you take, exactly same product is getting. So, this is a thermodynamic complex, it is a stable complex, irrespective of the positioning of the olefin we are going to get it. Now, of course, you have understood why it is happening, that is because it is a primary one. As we already tried to discuss, this primary alkyl species is more stable compared to the secondary one, and of course, compared to the tertiary one, secondary is more preferred over the tertiary one. But how exactly that is happening, let us try to look at. Of course, we have this example where we have again different olefin, 3 different olefin giving exactly same product. This is the thermodynamic product, this is the thermodynamic product, of course product, since this is the primary, okay, since this is primary and primary is more stable. Now, how it is exactly happening, let us try to draw the this Schwarz reagent one more time. So, this is your Schwarz reagents, and starting from this one, if you let us say take, of course, the first terminal olefin one, you know how it is happening, how you can explain, but with the secondary one, let us say try to take Sp2 zirconium, H and Cl, the olefin will coordinate, let us say here, over here methyl. Now, here first step would be the beta migratory insertion, right. Beta migratory insertion, you will get Sp2 zirconium chloro with a intermediate where this is forming, and from there on again further here you can see that this is the most important thing to note. So, this is beta migratory insertion, right. So, at the alpha position, at the beta position you have the hydride, this hydride is getting involved, right. This is alpha position, this is the position, this is the beta position, in this case after product formation at the beta position hydride is going on. So, that is the beta migratory insertion that is happening. Now, if you look at from this intermediate, of course, this is alpha, this is beta, but of course, this is also another beta. If you look at this product, this is alpha, this is beta. Now, from here, as you have seen in the previous general example, this is also a beta position. From this beta position you can have the beta hydride elimination, right. So, beta hydrogen elimination, particularly from this hydride from here, this methyl, right, and overall you are getting Sp2 zirconium and this intermediate, of course 1 2 3 4 5 6, one more carbon will be there, and this intermediate where you have again the opposite, the other beta one, not from this one, from this one due to the thermodynamic preference you will get that one, and what you overall see is then irrespective of the starting material, irrespective of the olefin positioning, you are able to transfer the bond from an internal to a terminal product, right. So, that is, I guess, it's literally very amazing. So, starting from an internal olefin, you are able to convert the internal olefin into the terminal olefin. anywhere that double bond is there, olefin is there, that olefinic double bond can be taken at the end or the terminal position. As soon as you have that, you have a very stable metal alkyl species. So, let us look at that product formation. From there on, of course, you are going to have the same product, that is Cp2, zirconium, chloro, and beta migratory insertion, in this case 1, 2, 3, 4, 5, 6, right. Beta migratory insertion you are going to get from there on. So, beta migratory insertion will occur to give you the same product. Remember, from the internal olefin you get a terminal olefin, and then you get the this primary alkyl. So, of course, the primary olefin itself will give the same product, thus internal olefin also giving the same product. Now, that having said that, you have perhaps realized that irrespective of the double bond position, you have the possibility of getting the more preferred metal alkyl species, because the double bond can be isomerized. That is how actually double bond isomerization occurs. This is there are a lot of example in the literature. Sometimes it is called the Zipper reaction. I mean, Zip, you just Zip unzip this reaction. You can see a lot of example with these cases, right. Now, we will particularly then try to tell you that it is possible to generalize this reactivity pattern, and the pattern is very simple, as we have discussed earlier. Pattern is primary is more stable, then secondary, and then tertiary. Of course, let us try to write down in terms of more of the olefin. We have the generalization, the stability is very simply, as we tried to say, metal primary, this is a primary one, okay, is more stable than metal secondary. This is the secondary, you have secondary, and you have metal alkyl species, that is over here. So, both this is both kinetic and thermodynamic product, kinetic and thermodynamic stability, thermodynamic mixed stability, both kinetic and thermodynamic stability. Rates of insertion, if you see rates of insertion, of course, I think it is no brainer. You would understand that, of course, the non substituted one is more stable, or the faster one, and then the mono substituted one, and then di substituted one, then of course tri substituted one, and finally tetra substituted one due to the steric region. Further steric region, as you would understand, it is going to be very less stable. So, the unsubstituted one like ethylene will be the most reactive, then the mono substituted one, then di substituted one, then tri substituted one, and then finally the tetra substituted one, right. Now, that would be the all for this beta migratory insertion and beta migratory elimination, or beta elimination in general, beta elimination. Now, we would like to then, of course, the other type of reaction that exists over there, where you do not have a migratory group associated with the metal, and but you end up getting almost the same product, or exactly actually the same result in terms of, let us say, olefin product formation. Now, it could also happen, that is what I am trying to say, that it could also happen that that migrating this beta migratory insertion, or let us say beta migratory elimination, specifically elimination reaction, this elimination step where the metal hydride is forming or metal alkyl could possibly form, this alkyl group may or may not bind with the metal center, and therefore, what you have left up with is the net result, and that is net result is the one where you have the olefin coordinated with the metal center, but that hydride is missing. In the alpha elimination or beta elimination, both the cases you have seen that, let us say alpha hydride elimination or beta hydride elimination, you have seen the hydride is attached or associated with the metal center upon elimination, but it could also possible that hydride could directly come out. Of course, these examples are not that very common, but it is feasible, it exists there where the hydride intermediate does not form due to a reason that there is no possibility of forming. Those are the reaction we call is abstraction, it abstracts directly. So, now I think in this category we would like to discuss alpha abstraction. We know the alpha elimination where the hydride gets associated, and the beta abstraction, that is the one where the beta migratory that beta group will not be associated with the metal center after the reaction, it will be directly abstracted, right. Of course, how are you going to differentiate? We will try to look at that. Let us try to discuss the alpha abstraction briefly today, and we will then move to the next class. So, alpha abstraction and beta abstraction, that is what the topic we would like to discuss. Again, it is extremely crucial to understand that there is a subtle difference. What is the alpha abstraction? Alpha abstraction, you have a metal, let us say R alkyl, it could be hydride as well. Okay. Okay. Now, this metal is taking and giving directly, let us say this is as base, right. Directly you have a metal carbene species plus RH, no change in electron count, as you can see, no change in electron count. If this one was n electron, it will be also n electron. Just to remind you about the alpha elimination, it is important just to really get the feeling of it. You have, let us say metal, the same type of species MH over there. If you have this compound, the alpha elimination will give you the product where the same exactly same product you are going to get, but this carbene product that comes with the hydride in this case. So, this alpha position hydride is moving to metal in this case. In this case, there is no association of the hydride with the metal center. So, it directly comes out as the RH. So, there, as you can see, there is a very subtle difference between this alpha abstraction and alpha elimination. You have seen the example. Now, we will like to discuss in the next class how this example will construct a very good mechanistic view, or why we would like to why this beta abstraction or alpha abstraction is feasible, why their elimination and alpha elimination and beta elimination cannot happen in certain case. So, that will be discussed in the next class. Till then, you guys keep on reading and send us the question that you may have. Thank you very much.